Well, that was fast.
Everybody should know the drill by now. We're getting a lot of practice at these. All right, well, thanks very much for everybody for taking time out of their day to come and hear another one of our excellent graduating students. So this will be the talk by Aaron Bray, who will be talking about Galactic Conformity, which I will let him explain what that is. But Aaron came to us from Yale in 2010, and I've been very happy to have him in my group. He's actually been working a lot with me, but also with Lawrence Fernquist, who unfortunately couldn't be here today. But Aaron has been working on a wide range of methods, from observational data all into theoretical predictions from hydro simulations. And I think his work is remarkable in the area of experimental design. So what I mean by this is that one of the big challenges in understanding how galaxies form is the fact that we only get to see little snapshots, single snapshots in time, and we're left to try to piece together how that picture evolves, how to see the movie from a bunch of disconnected stills. And doing this and being able to connect that to the actual underlying theory is a challenging process. We don't get to tailor our experiments to design our experiments as carefully as we would like, and we're left with what the data can actually tell us. And Aaron has been really very vigorous at trying to figure out, when he measures something in the data set, what does this actually allow us to infer in the context of the theories. Doing this work has been, he'll tell you about the results today. I think he will have the pedagogical good sense to spare you some of the agonizing details of dealing with real survey data. But we spent quite a long time doing that. And I also want to just say before I give the floor to him that he's been an excellent teacher as well. He got a certificate of distinction in teaching in Astro 17, and I want to also thank him for all of his role in that course. So without further ado, let's hear from Aaron.
All right, thank you very much, Daniel. I appreciate that. So let's get started. Today I'm going to be telling you about my work over the past 6 years here at Harvard, looking at galactic conformity via small-scale clustering and simulations and surveys. But before I do, obviously, it's not just my time that's gone into this, but a lot of other people's time over many, many years. And first and foremost, let me thank Daniel again. He's been an invaluable mentor, an incredibly kind mentor, one who cares an immense amount about doing careful, rigorous science, and also one who really understands what it means to be a person doing science and not just the science, and he sees to both part of you, and for that I'm immensely grateful. Lars Hernquist, despite having been Daniel's student for 6 years, I've almost effectively also been Lars' student, and he's been, unfortunately, he can't be here today, but he has welcomed me into his group with open arms, and I've learned a lot by being in both sort of more observational, data-driven side and large-scale surveys, and also working with hydro simulations, and also just hearing about that for several years at his group meetings before I even started working with him more. In particular, also Annalisa Pilipich, who now has a job in Germany and therefore is getting ready to launch her own group at MPIA, and therefore who can't be here today as well. But she has been an integral member working with on the Illustris data set. I'd like to thank my committee for providing advice over the last several years, and also now to Jeremy Tinker for being here from the real city, New York. And, the last 6 years would have been very, very different. I think everybody here knows, without Peg and Nina and Rob, and in my case, Lisa and Mark, who are just amazing and wonderful administrators. They make everything run smoothly, and they're always there to chat with and talk with when things get tough. And and then everybody, both in my group. I have a lot of people in my group. I have a lot of people not in my group. There's so many of you guys, and like Jason said, let's skip through here before I realize I forgot somebody. Thank you all so very much. But I will highlight Marla Jiha, Ricardo Munoz, and Charles Balin, people I worked with while I was an undergraduate at Yale, who really got me into astronomy. My in-laws, Joanna and David Jerrison, who are from the hinterlands of Belmont, Massachusetts, and therefore, since my family is across the country and can't always be here for holidays and for hikes, I have joined them, and we have done some really amazing stuff together, celebrating holidays and getting out into the mountains, which is always great. My late grandfather, Ralph Bray, who probably more than anybody is why I ended up going into science. He was in semiconductor physics, solid state in the 1940s, and by the time he was this age, he was mostly interested in cosmology, and we talked a lot about it at a fairly young age, usually while playing chess. And I'm sorry he can't be here. It's been a while, but I still am. And my parents and my brother, who have been with me this entire time, and most of all, to Elizabeth, my wife, who for the past 10 years has been my constant companion, discussing science, discussing politics, and getting out to some really gorgeous mountains as well. So without further ado, I'm going to start telling you about galactic conformity via small-scale clustering and simulations and surveys. So you're going to have to bear with me for a moment before I tell you exactly what galactic conformity is. However, what I'm really talking to you about today are galaxies and their existential journey. Because really, what we want to know is, why do they live? Why do they form stars? Why do they die? Why does that star formation shut off? Where do they go? Where are they located in the physical structure of a lambda CDM cosmology? And please, just tell me why. Why do they go where they go? So, thanks to hair. Now, the driving force behind where galaxies form that we know is the fact that in a lambda CDM universe, galaxies are connected to their dark matter halos. And this means that because they're inextricably linked with the underlying dark matter, you end up with stellar mass tracing out halo mass. In general, brighter, larger galaxies are found in larger halos, and fainter galaxies are found in fainter overdensities of dark matter. What this means from a scientific perspective is that there's actually a fairly tight relationship between stellar mass, between stellar mass and halo mass, and this is not observable data, but this is a fit to data, and you can see that there's actually a fairly tight relationship. But ultimately, there is scatter, and there are different types of galaxies. And one of the things we like to understand is where the scatter is coming from. Why do some have more? And ultimately, if there are differences between galaxies that are quenched and galaxies that are not quenched, what can that tell us about the physical processes that are driving galaxy formation and driving galaxy evolution over time? So I'm going to be showing a number of plots that have two-point correlation functions, so we need to get this out of the way first, even before we get to galactic conformity. And the two-point correlation function is just the excess probability of finding a galaxy at some distance r compared to a random distribution. And these galaxies are more highly clustered than these. And so what you can have is either, as I said, it's the excess probability. And you can either do this in 3D, in real space, and this is represented as FC of R. You can do this as an angular deprojection on the sky, because ultimately that's how we measure things. And if you know the distance to an object, you can also measure this as an excess probability at some projected radius from a particular galaxy. Now, as I told you, the question is whether or not galaxies and their formation can be understood in the context mostly of their halo mass. And I won't get into the nitty-gritty details of exactly of these models, But suffice to say that models do quite a good job fitting the clustering data. So this is WP, projected correlation function, as a function of radius, even as a function of luminosity. And this is from SDSS a couple of years ago. But when you try to divide things up into red and blue galaxies, the fits start to become less good. And these fits are still assuming there is no specific relationship other than luminosity. And so the question is why is this? Why would this be more difficult to predict than just luminosity dependence? Well, we don't fully understand the transition from star-forming blue galaxies to quenched red galaxies. We don't understand why we go from galaxies that look like this to this, and of course it's not a completely monotonic process. More gas can come in, but over time, the overall quench fractions of galaxies does increase over time. So the goal is to use the small-scale clustering of quenched and star-forming galaxies to use their correlations between each other spatially to better understand the underlying physical causes of galaxy evolution. So, galactic conformity. What is galactic conformity? The term itself is about now a decade old, but let's explain it first with a cartoon. I've already said that the main driver of galaxy formation is the mass of the halo the galaxy is growing in. So what we're going to do now is we're going to compare two different galaxies that are in the same mass halos. And I'm going to call these the primary galaxies. There's a red primary galaxy with little star formation. There's a blue primary galaxy with a lot of ongoing star formation. And then there's all the galaxies around it. What you'll notice is that at least close to the galaxy, on average, these red galaxies, primary galaxies, have more red secondary galaxies around them than the blue one. So this is to say that the color of the secondary galaxies, on average, so you're doing this over a large data set and taking the average, whether it's the mean or the median, this matters, unfortunately, conforms to that of the primary galaxy at some fixed primary mass. And that mass, as I said, we would really like it to be halo mass. But of course, since it's dark matter, sometimes we have to rely on proxies for that halo mass, whether that be stellar mass or group luminosity. And we care about, because it matters for the physics involved, whether this galactic conformity occurs for satellites around their central halos, where we expect that perhaps baryonic processes, gas, ram pressure stripping, AGN might have more of an effect. So the central's around a particular central host galaxy. And you can see here there's a larger quench fraction. And so conformity basically refers to the fact that this quench fraction of 80% is larger than this quench fraction of 25%. It's not a majority. So this number could also be 40%, and this could be 20%, and we would still be saying that there was galactic conformity there. Because overall, the average quench fraction is also a product of just the redshift of the universe where we are now, since there is evolution of quench fraction with time. And we want to know how far does this galactic conformity extend. So beyond the virial radius, these models that predict where galaxies should form are a function of the halo mass. But there's a lot more out there. There's larger scale environment. There's interaction between halos. And so one of the things we can do is look at the relative quench fractions and thus understand galactic conformity at distances that are much larger. So instead of looking at distances sort of underneath somewhere between, let's say, 250 kiloparsecs to a megaparsec, depending on the size of the halo mass, we can be looking out even to 10 megaparsecs. So, as I said, galactic conformity is about 10 years old, and it was first mentioned as such in SDSS. And what's plotted here is the late type fraction, so basically blue spiral galaxies on the y-axis, in different luminosity bins for the primary galaxy. And let's just focus on the one in the top left. So in this particular luminosity bin, they've shown that blue late type centrals have a larger percentage of blue late type satellites around them than the early type. So this is an example of galactic conformity, and they've shown this at various halo masses, where the halo masses, as I said, lest you be confused to think that somehow someone has actually measured the actual mass of the halo based on a group catalog, based on the total luminosity of that group. So this is just one of the ways in which you can attempt to infer halo mass. And so in that caption, a phenomenon we term galactic conformity, and like some but not all terms like this one actually stuck. Now, more recently, there's been work that's looked at a similar effect, but at larger radii. So instead of just looking in the particular halos, you'll see that on this plot, the radial bins go out to 4 megaparsecs. And on the y-axis, this gets a little tricky, but it's the log specific star formation rate, so the amount of stars that are being formed in neighboring galaxies. So a higher number means there are more stars being formed. And what I want you to take away from this plot, which is showing the average specific star formation rate of neighbors around individuals, primary galaxies, is that these galaxies here, for example, are the 50% most quenched primary galaxies. So the black and the red lines are those that have already themselves basically stopped forming stars. And you will see that on average, their neighbors have also stopped forming stars on average more. So it's about 0.4 dex difference between the 50% most quenched and the more star-forming neighbor and the more star-forming primaries. So let me just reiterate that I've talked about contributing physical processes. I said that halo mass is the main driver, and that can be due to a combination perhaps of just buildup over time of mergers and gas being funneled to the center and used up. It can also be grand pressure stripping. It can be that gas falling into galaxies is shocked and never cools down to be able to form stars. But then there's something else that I would like to be able to test, and that's this thing called assembly bias. And that's the idea that the galaxies actually know a little bit about how the matter in them was built up. So when did the halo in which they're actually living now, when did it form it? Not just what is their mass now, but something about the history. And that can also include the merger rate, the last merger, other large-scale environment, and other multi-halo interactions having to do with gravity and sort of the large-scale tidal field in which these galaxies form. An alternative possibility, and one that has been proposed in the literature, is AGN feedback, other forms of sort of preheating, whereby AGN could heat up the gas at some particular scale at some time, and thus that gas is hotter in some large region on the sky. And so one of the things that I would like to be able to test is sort of to distinguish between these two. Now, halo assembly bias is this idea that clustering properties of dark matter halos, for example, in dark matter only simulations, is dependent on when these halos form. And this has been well studied and seen in a lot of dark matter simulations. And this just has to do with that the collapse mass changes over time of the dark matter halos. And so ones that form earlier can end up being in environments where they are no longer accreting matter if there are larger halos nearby. And it is possible, therefore, that not only would they not accrete as much dark matter over time, but perhaps they would accrete less cold gas over time. On the other hand, this doesn't necessarily follow from halo assembly bias. It could be true that given the large number of baryonic processes, as I said, AGN feedback, gas, that we sort of lose sight of where we actually came from. And all we know in the end, that things average out and that the mass is all that matters, its current state. So now I'm going to talk to you about contribution using the Illustris simulation. And I will explain to you first why this is such a great simulation. First off, this is a very large, state-of-the-art cosmological simulation with fully implemented hydrodynamics. That means that we have sufficient galaxies, about 20,000, with mass greater than 2 times 10 to the 9 stellar mass, with which to do statistics on. And at the same time, unlike using more prescriptive models, we get to see whether or not the galactic conformity that we're interested in arises naturally. After all, these simulations are essentially tuned to reproduce single-point statistics, things like the stellar halo mass relation. No one went in and said, okay, let's make Illustris work out so that we have galactic conformity. And thus, we can actually test by looking at that whether this is actually something very natural or whether perhaps we need to add more and additional physics. So, and as I said, it really matters in terms of experimental design. When you see something, why are you seeing it? And being able to do this self-consistently in a dark matter-only simulation that has hydro on top of it means that not only do you know the stellar masses of the galaxies, their environment, but you also know their halo masses. And so you get to see those two things together. As I said, you don't have any of this confusion about needing to use group luminosity, for example, to infer the halo mass. So also I should say that Illustris produces, and you've seen many pictures like this before from many people in the Hernquist group, a full range of ellipticals and spiral galaxies, as well as irregular, messy-looking galaxies that are the product of mergers or other types of disruptions. And so we hope that we are, in fact, looking at a representation of the real universe when we use these simulations. So let's cut to the chase. I find galactic conformity in the Illustris simulation. And let's go through this plot in more detail and then move on to slightly more complicated plots. So on the y-axis, I have plotted quench fraction. Again, this is the quench fraction of neighboring galaxies around my primary selection. So I require some mass threshold above which I only include about 18, 20,000 galaxies. And then I split those primary galaxies into both star-forming and quenched galaxies. And then I look at their neighbors. I also apply additional isolation criteria and cuts to try to compare with the literature. But let's focus instead just on this and realizing that the quench fraction around quenched primaries is significantly higher than around star-forming primaries. And you'll notice immediately that there is basically two regimes. There's one regime that goes out to about 3 megaparsecs, in which it's more than, in which it's almost a factor of 2 higher in the inner radius, and then beyond 3 megaparsecs, where it sort of plateaus. And it goes out to about 10 megaparsecs, which is well beyond the virial radius of a galaxy of the stellar mass. It doesn't go out quite as far for larger mass halos, and I'll get to that more in a sec. So now you see lots of these plots, and let me go over at least one of them again. So I'm showing in the top left the same one, and that is to say for the lowest mass galaxy masses, we find that the conformity is greatest. And then as the mass of the stellar mass of the galaxy increases, it decreases, quite rapidly, in fact. But what we've also done, as I said, this is very important, is that if we bin them in terms of halo mass, we also see a similar thing, where if we look at the halo masses of where these galaxies are located, these don't match up exactly. I mean, there's a large spread in terms of stellar to halo mass ratio, but we do see that in larger halo masses, the galactic conformity signal drops off fairly rapidly. And so this is interesting. And so now we want to go back and say, all right, so we see this signal, but why? What is the simplest possible explanation? Is without invoking additional physics, can we understand what's going on here? And so I'm going to take a note from the literature and calculate halo ages for each of these dark matter halos in which these galaxies exist. And I can compile a full mass accretion history over time from the sublink tree catalog from Vicente Rodriguez Gomez, who will be speaking here a little bit later. And I will find the earliest redshift at which a given fraction of a halo has formed and call that the formation time of that particular halo. And What this allows you to do is actually to calculate something very similar to galactic conformity, but for halos instead. Rather than asking whether red galaxies are preferentially located near other red galaxies, we can ask whether older halos are preferentially located around older primaries. And I'm not surprised to see, because this has been seen in larger dark matter only simulations. The answer is yes. And it shows a similar qualitative view in which it's much stronger out to about 4 megaparsecs and then decreases. However, you'll see that for these stellar masses, and when I say stellar mass, I mean the stellar mass of the galaxy that actually is in that halo. It doesn't decrease nearly as rapidly. So that tells us that something else is going on. And likewise, I've checked, and just you can see that the dotted line is showing what happens when you look into dark matter only simulation. So I just did a sanity check to make sure that there weren't large differences in the dark matter at these scales, dark matter at these scales, because Illustris is a companion simulation that has no baryons in it. So galactic conformity appears to be strongly linked to this dark matter conformity. And the reason, at a very simple level, and one that has been suggested before, is that the color is related to the halo age. So if you look in the top left, the redder galaxies tend to be preferentially found in older halos with older look-back times. And what you see are two different plots. One, the median trend in the Illustris data, and the other in a semi-empirical model in which, well, this is what would happen if you put the reddest galaxy in the oldest halo, the next reddest galaxy in the next oldest halo. And you'll see that these track pretty well until you get to higher masses. So at which point there's a large difference between what the galaxies in Illustris and what would happen if you assigned it based on this way. So now I'm going to tell you that we want to understand if this really works. I've just shown you some pictures here, and now I'm going to go through it slightly more in depth and show you that if you now use a method called abundance matching, which assigns galaxy properties to dark matter only halos, you can actually see that this prediction doesn't work if you don't use something other than halo mass. So in abundance matching, you assign the most massive galaxy to the most massive halo and move on down. And we also added a scatter to this relationship based on empirical studies. And we include both centrals and satellites, where our halo mass is the maximum of the accretion history. We want satellite galaxies which may have been stripped after accreting onto their halo to be considered on equal footing. And if you just have this mass-only model, and then you reassign, you scramble where the galaxies are located in the Illustris simulation. So instead of looking and measuring galactic conformity in the simulation as is, you assign them instead based on this empirical approach. The signal is entirely washed out, which is not that surprising because this empirical approach knows nothing about the colors of the halo. So you shouldn't be surprised that the quench fraction around these galaxies is not actually different. Now, what if we include something about the color? What if we now assign color based on the formation times of the halo, as we saw actually does also arise naturally in the Illustris simulation? So now we've related color to the age of these halos. We've created some assembly bias, and now we've done this on top of the abundance matching. So we first apply galaxies such that their masses are based on the halo mass, and then we go on and apply color based on in small bins and stellar mass. And when we do that, we actually immediately recover something that qualitatively is very similar to what we had before, the same relationship. So we basically now have in a parsimonious sense, just these two quantities were sufficient to reestablish a galactic conformity signal, like the one that arises naturally out of the Illustris hydrodynamic simulation. So I've told you a little story where with only a single extra parameter above mass, you can basically go from the Illustris measurement to washing it out if you only consider mass, to reestablishing it if you include abundance and age matching. So I told you before that there were one halo and two halo terms, that we were interested both sort of in for satellites and their own centrals, as well as satellites and also perhaps centrals at much larger radii. And I also showed that the virial radius of these halos is potentially very, very small. So actually, basically everything that I'm looking at, especially for these low mass halos, is in fact this two halo term. And yet, we were a little bit surprised that with satellites included, if you just measure using all of the galaxies in Illustris, you see this quench fraction go from being quite high and then it plateaus. If instead you redo the calculation with no satellites included, so we have a halo finder which identifies things as either centrals, the most massive galaxies effectively in their halo, or satellites, and you eliminate all the satellites, the conformity signal falls dramatically. So this is telling you that there is something essentially quite special about satellites as well in contributing to this signal. However, it is not to say it disappears entirely. And so you might have thought naively from the cartoon I showed earlier that the satellites would only be in effect actually at small scales with near their own satellite. But actually that's not the case. It's the larger scale effect going out to 10 megaparsec that disappears if you only include central galaxies. And this is also seen in the halo conformity as well. So you have a much smaller effect. At large scales, it's almost entirely the satellites, and in that case, it's satellites of other centrals. And at small scales, you actually have about a 50-50, sort of the quench fraction is half coming from the centrals and half coming from the satellites. All right, well, so I've shown you that in a dark matter only simulation that has hydro included in it and is thus fully solving both n-body and hydrodynamics, that we find a galactic conformity signal at z of 0 out to nearly 10 megaparsecs, at least for the least massive galaxies. Now I want to transition into the real universe and try to understand this even better by using observations from the number of large photometric and spectroscopic surveys that have been developed and run over the past decade and a half. So the project that I worked on is called the PRIMUS Redshift survey. This is the PRISM multi-object survey and has a lovely name. It's actually just a large prism rather than being a grism or some other type of higher resolution element, but it gets good spectroscopy sufficient for doing large scale structure measurements. We don't need to be able to see the metallicity of every star. So actually we end up getting instead a lot of galaxy redshifts. These were obtained at Las Campanas in less time. And one of the key things for the methods that I'll be talking about in a sec is that it overlaps with a lot of multi-wavelength photometry, which means that one can derive stellar masses for these PRIMUS galaxies, and one can also use the clustering, not only of PRIMUS galaxies, which other people in the group have done, but one can cross-correlate galaxies, and I'll explain how, in PRIMUS with the photometry in those same fields, which is a lot larger of a sample. Whereas I'm going to be talking about studies that use approximately 60,000 galaxies, sort of the ones that were selected from this parent sample. There is instead hundreds of thousands, and in some fields, over 1 million photometric galaxies, which in theory we can cross-correlate and get correlations functions from. So these are some of the fields. As I said, in the colors, which are arbitrary and don't have any particular meaning except to show that we divide it up into various subsamples for calculating errors. The colors are PRIMUS galaxies. These have redshifts. The black galaxies are basically both under and all around them, and these are photometric galaxies that do not have redshifts known for them. And all the white holes, as Daniel said, are a couple years of work. So let me explain to you how we can use photometric galaxies to do a better job understanding the color dependence and the luminosity dependence of galaxy clustering and thus galaxy formation. This is a particular field, and once again, you see that there are a lot more galaxies in this field than there are PRIMUS galaxies. So these are the PRIMUS galaxies now. They're beautiful. But we do know the redshift. But they're also quite sparse. So if we wanted to understand the clustering of red galaxies, we might end up being in the shot noise limit if we wanted to start dividing these things, not just into all red galaxies, but brighter red galaxies, fainter red galaxies. Same thing with the blue galaxies. If you want to start looking at things and doing more precise measurements as a function of luminosity and of color, you quickly run out of statistical power. So, what if we wanted to understand the environments of these galaxies, and we could use something else, like the giant imaging catalogs, which are also present? And as you see, as represented by them being black, we don't know their redshifts, but that's okay. And that's okay because to make things as simple as possible, in the end, galaxies which are not located at the same redshift as a galaxy with a known redshift are not going to have any physical inherent correlations. So it is possible to statistically subtract out the effect of these galaxies. So anything that is foreground contamination or background contamination, while annoying and will increase the error, your noise floor, does not affect the correlation function unless there are So what we actually end up getting then is a deprojected overdensity, where I can calculate the galaxy overdensity as a pairwise summation over spectroscopic and photometric galaxies. And this has been used prior with SDSS to look at red luminous galaxies, luminous red galaxies, LRGs. And instead, this time we're using it to be able to subdivide and look at, as I said, a wide range of redshifts and luminosities at the same time. And out of this, I am able to derive a 3D spatial correlation function of the PRIMUS galaxies, which is effectively the same thing as an overdensity around these galaxies. So, more specifically, what you do is you assume that all of the photometric galaxies in your sample are at the correct redshift, and then actually apply an absolute magnitude cut, because now for a moment we've assumed that we know the absolute magnitude, since we know the distance, and then have some relatively fixed tracer sample. And so we are calculating the overdensity around each galaxy in terms of the number of photometric galaxies that are actually correlated with that galaxy. And as I said before, background and foreground galaxies do not impact the correlation function. So, first result plot, you see here on the y-axis r squared times the correlation function. This is just to flatten this out and get a better sense for scale. Red galaxies are, as has been seen at low redshift, much more strongly correlated by a factor of 3 to 4 than blue galaxies, particularly here at this transition region, which likely has to do with the fact that the blue galaxies are in smaller halos than the red galaxies, and green galaxies lie somewhere in between. As I said, we also can look at the luminosity dependence. And so here I'm showing the clustering again at a couple of specific scales instead of over scales, but for different luminosities. So this is absolute G-band in SDSS. And you'll see that at different scales, the luminosity dependence actually changes. So that was one of the things we found, which was there was actually very little luminosity dependence at these intermediate scales of 250 to 500 kiloparsecs, whereas there was significantly more luminosity dependence at 125 kiloparsecs and smaller. But even beyond that, you can see a couple of things. One of which is that the red galaxies and the blue galaxies do not have the same luminosity dependence. It's much stronger for the blue galaxies. And we'll explore that more with the additional galactic conformity worry. So, luminosity dependence is neither monotonic, nor is it scale invariant. And both of these things need to be considered when fitting models that include color of galaxies. So, what I'm working on now and have now found is that using the same methodology that has been built up with the PRIMUS catalog, we can also look at galactic conformity. And we do this by making a few changes to our methodology. And we do this because a lot of the work that's been done with spectroscopic samples has been done at low redshift. So the stuff from Simone Wyman, the stuff from Kaufman groups, has been done at low redshift. And only very recently are the effects of assembly bias starting to be explored at much higher redshift. So in SDSS, around for more higher mass galaxies, around Z of 0.3, 0.5, and using photometric catalogs only at much higher redshift. So people are now beginning to look at galactic conformity out to even redshift of 2, but with a lot more uncertainties having to do with the fact that there aren't spectroscopic redshifts for all of these galaxies, and these tend to be very small samples. So there tend to be, even 3 or 4 times fewer galaxies, if not more, than the sample that we're working with. So PRIMUS can probe the conformity signal, in particular for fainter galaxies, in the 1 halo regime, and then starting to get into the 2 halo regime, because as I showed, I can start looking out to about 1 to 2 megaparsecs, which for low mass halos is beyond the virial radius. So instead of dividing primary galaxies up by luminosity, I'm now using, as I said, stellar mass. And that's because we have this great multi-wavelength photometry, so you can infer stellar masses So John Mastakis did this for most of the galaxies using the IR and UV in the field of those galaxies. And as you'll see, that we're limited a little bit by the completeness, obviously, due to the flux limits of the survey. At lower redshift, you can get down to lower masses where there are both red and blue galaxies. We need the completeness not only of all the galaxies, but the completeness of both red and blue galaxies. Because if we're going to compare these things, we actually need substantial populations of both. And then in addition, we go out of our way and to make sure that since the signal tends to be so small, you need to weight them so that they actually are exactly the same in number density. And so now for the secondary sample, instead of doing a luminosity cut, we can use a stellar mass cut. And the big addition is that instead of just looking at overdensities around PRIMUS galaxies as a function of how many galaxies you can do this twice. You can say how many galaxies are there overall, and how many galaxies are there that meet some definition of red. And using those two things, for small scales, we can calculate the red fraction as the quotient of the overdensities between these two photometric samples. So we basically have a overdensity of red galaxies around red galaxies, of all galaxies around red galaxies, of all galaxies around blue galaxies, and red galaxies around blue galaxies. And I'm just showing here the correlation functions for each of these. And as you can see, in general, the samples calculated with all are higher because the red samples are a subset of the overall one. And then you'll see also, and this is pretty important for understanding what's going on, the quenched galaxies at fixed mass are in more overdense environments, period. We've already made this cut in redshift and in stellar mass. But nonetheless, there are simply more galaxies. It is more overdense around these red galaxies, which means that they probably trace out higher mass dark matter halos. And so that means that at least some of any conformity signaling you're seeing is likely going to be attributed to that rather than necessarily some additional assembly bias. But we do see conformity. So again, I'm showing you a particular stellar mass and redshift sample. And you'll see that out to about 0.8, 0.9 megaparsecs, the red galaxies preferentially have red galaxies around them compared to the blue galaxies. And it's a fairly significant effect. But even going up just a little in mass, the conformity signal decreases for higher mass primaries, which actually is what we would expect if this is due to assembly bias. And you'll also notice between these two plots, flashback, is that the overall quench fraction around red galaxies does not change that much between the two mass spins. And that's actually correlates with what we found in the initial PRIMUS results, which is that there is not a large difference in overdensity at intermediate luminosities in the red galaxy population, but there's a stronger luminosity dependence among the blue galaxies. So here, most of the difference in conformity is because the blue galaxies actually have much larger red fractions when they go up in stellar mass, rather than the red galaxies falling. We can also look at this by redshift, as I said. So you'll see here that at least out to z of 0.6, we see that this conformity signal exists for both lower and intermediate redshift bins that we have available to us. And here again, we're constrained by the fact, as I said, there is a flux limit to the sample, and then therefore can't go to as low of masses for higher mass. So, which then limits. If you go one step further, I can show you a slightly higher mass sample, and this is where things get complicated. But also, this is also interesting because it gives us a lot of further things to explore. At the highest redshifts, the signal is definitely smaller than at the lower redshifts, but it's also not monotonic in the way that I would have expected. And this is something I have to further understand, because what we see here on the left is that there is a very strong mass dependence at the lower redshifts. But in the intermediate redshift regime, actually, there's a conformity signal in all of the mass bins which we probe. And then finally, at the higher mass bins, it disappears once again. So figuring out exactly what is causing this is not something that I yet fully understand. Moreover, in order to be able to even make these measurements at the highest redshifts, we need to include a sample of tracer photometric galaxies that have higher secondary mass. So as I've already said, there may be a mass dependence to this, but in order to have sufficient number counts of the secondary galaxies, we need to raise the mass because there aren't as many faint galaxies, which means that if the signal is going down, we don't necessarily know if that's because of a mass dependence or a redshift dependence. So, before I get to the summary, I would say that I think the biggest thing to take away from here is that it is possible still that the signal is being caused somewhat by assembly bias, but at the very least, halo mass is still even in the PRIMUS galaxies, is definitely the predominant factor in this conformity signal. And which is difficult because it also means that in order to reduce the error bars and to get even better measurements, we will need even larger samples. We will need, we need to use SDSS3, we need to use SDSS4. And one of the limitations of this survey is that because PRIMUS has somewhat small fields, each one, even though it covers 10 square degrees, each one only covers maybe half a degree or a couple of degrees at most. You're limited in how far out you can look. So in the same survey, you can't actually go out as far as it would like in exploring this 2-halo conformity. As in Illustris, we were able to explore out to 10 megaparsecs, but especially at low redshift, it's not possible to explore out to 10 megaparsecs with this methodology. So I've told you that using the Illustris simulation, I've presented evidence that galactic conformity naturally rises and extends beyond the virial radius, and that it can be explained in a parsimonious manner by a combination of halo-age conformity and the color-halo-age relation. In the PRIMUS redshift survey, I've additionally presented an analysis of the interplay between luminosity and color and scale dependence of small-scale clustering. And finally, I've showed how cross-correlations between spectroscopic and photometric catalogs can be used to measure galactic conformity over a range of stellar masses and redshifts. And this is a topic that we are still exploring and one that I think will be very interesting in the years ahead. So thank you very much.
Okay, we have time for some questions.
Aaron, really nice talk. I've seen you give a lot of talks, but I think this was the best one so far.
Thank you, Zach.
I'm excited to see this all come together. So, on that note of coming together, it's really nice that in Illustris you found that actually you have basically one extra parameter and you can explain the conformity and it matches the actual result of the simulation. But how does this connect to the PRIMUS? Is it basically correct to say that in PRIMUS you couldn't add just one extra parameter and explain what you're seeing? Does PRIMUS agree with Illustris? Like, how do we put those things together?
So much of the signal we're seeing in PRIMUS is, of course, as I said, at smaller radii. And I've focused on the two things due to what is possible, more on the 2-halo conformity, so is how far out does it go in Illustris, whereas in PRIMUS, I'm only looking out to 2 megaparsecs. But if various of the physical motivations for assembly bias are correct, and that what's causing older halos to have redder galaxies is that smaller halos are starved of gas and dark matter, basically any accretion of material over time, then, at some point, things that are in this 2-halo regime, satellites accrete. So the two are related. And if we didn't see any, if we saw no conformity in the 1-halo regime, I think that would be a sign that there also was not a large 2-halo conformity term. Because you would expect if you have quenched galaxies out at multiple megaparsecs and they eventually accrete onto other quenched galaxies, you would expect that to already be the case.
So, Aaron, related to the last point, you have to have this kind of anchored spectroscopic sample to look at the signal, or can you do this purely with photometric redshift data? So if you had, for example, 10 years from now, 15 years from now, the full LSST catalog of galaxies, could you do all of this with just that sample?
I mean, obviously, people are doing it with photometric galaxies, and I think those studies are really, really interesting. If one wants, I'm seeing a fairly dramatic difference between, the mass dependence in between 0.2 and 0.4 in Redshift, and 0.4 and 0.6, 0.6 and 0.8, and there's even just between the best, the best photometric, like multi-band photometric redshifts and spectroscopic redshifts, there's still a factor of many, at least a factor of, R of 4, the spectroscopic resolution of PRIMUS is about 40. So if you were going to look at redshift trends especially, I think that's difficult to do with photometric galaxies. I mean, more importantly, I think the biggest improvement that can be made is to have better halo mass metrics, because I think that actually is the limiting factor. I mean, one can use galaxies as tracers and say that if you have more galaxies at fixed stellar mass, that means the halo mass is larger, and you have lensing at higher masses. But the signal is expected to be strongest at lower masses. And so especially going out to higher redshift, where these things are harder to observe, you just need deeper and deeper imaging.
Charles, this is a follow-up to Rito's question. Given your reservations about photometric redshifts, is there a natural successor coming up to PRIMUS that will actually address your concern?
not doing exactly this. I mean, there's already been sort of right at the lowest mass galaxies that can be done in the galaxy masses of 9.5 cannot currently be done in SDSS 3, but slightly higher mass ones can. And so I think, obviously, because the interest is not just in looking at galactic conformity, but more generally, we're interested in assembly bias and whether history matters for the colors of galaxies. There's been a lot of really amazing work the last couple of years in higher masses. This trend is expected to effectively reverse at the highest masses. So if old halos are overclustered for low mass galaxies, younger halos are overcluttered for higher mass. And that's a lot easier to observe because you can use X-ray data to get masses. You can use lensing to potentially get masses.
Any last question? Okay, well, let's thank Aaron again.
Well, the fifth time would have been the charm, but all right, well.
Okay, so I'll just take. Let's.
What do you want to do? I mean,
Yeah, we'll head down there now.
Charles will get. You know where we are, right?
Yeah, we're in Pratt.
Okay.
So just 15 minutes or something. It's not. Don't.
Yeah, no. I mean, I'll aim to be down. Can I aim to be down there at 2:45? All right, great. See you very shortly.
Not my best talk ever. So, despite Zach's hilarious remarks, that was not the best or the worst talk he's ever given.
It was great. We're done.
All right.
Now you have to do something really fun. Anyway, thanks for inviting me. Sorry your parents couldn't be here.
Oh, yeah.
Oh well. What an ordeal.
The funny part is, like, 4 times a day, 5
That's fine.
Thank you.
This part was actually the scariest part for me because you have the pressure of the members in the eyes.
Oh, there you go. I'm terrified.
Fine. You'll be fine.
Really know what you're
talking about this.